Okay, so welcome everyone to this seminar number 10 in the series. So we're going to be talking a little bit about fundamentals of deep neural networks, and this is kind of like loosely based on a few different papers actually, which are in the references. So just an overview of today's talk. So this is a recap. We'll start with a recap of neural networks, which we had a few slides about that. Then talk about deep neural networks. So basically modeling the theory. So what is the idea behind them? What are they trying to achieve? Some fundamentals actually in terms of empirical risk minimization. How do they fit within the context of learnability? And then finally talk about the training process. How do we do the training? So basically cover some back propagation, and we will get a little bit messy with the analysis, with the derivations for back propagation. So hopefully this will go smoothly. And finally, also talk about some different training paradigms that people have thought about actually. And this is, as I said, this is based on a book actually, on a book and a couple of tutorials actually. This is coming up in the references. Okay, so just a recap of neural networks. This came up actually, I think in seminar 1 or something. So basically, it's based on the perceptron model, which is like the smallest atom or the smallest unit in neural networks. So basically, they were proposed for binary classification, usually for classification and prediction. So basically, you have a weight per each input. You have n inputs, and then you scale each input by a weight, basically. So very simple. And then you apply some sort of nonlinearity, sigma, right? And then sigma is basically this called nonlinearity, or it's also called activation function, etc. So basically, in a sense, it's a linear regression. The perceptron is a linear regression, and then which is followed by an activation function. Okay, so then this was the perceptron. This is like one unit, as we were saying. So the idea for deep multi-layer neural networks, also deep neural networks, is exactly. So what happens when you stack them together? Actually, when you connect the output from one, and then you connect the output from one, and then connect it to the input of another one. And this is actually exactly what happens, right? So here, this is your input layer, right? Each input layer, right? Each perceptron, you can connect it to another layer, which is called the first hidden layer, and then you have weights, right? So this is, let me move a bit. Yeah. So this is actually weights W1, which kind of connect the input layer to the hidden layer 1. You can have many hidden layers, right? So you can have hidden layer 1 and hidden layer 2, and then the weights that connect these two you can call it W2. We can have another one, W3, and then we have the output, actually, the output layer, right? So this is so this is kind of the motivation. So this is how perceptrons are the basis of these multi-layer networks. Okay. Now let's talk a little bit about the modeling, actually. So this is, I'm a signal processing guy, so basically I like to think about these neural networks as like layers of blocks and filters, right? So for instance, if we think about a deep neural network with J layers, capital J, so we can, it makes sense to think about it in the context of a cascade of J filters plus an activation function, right? So if we start with, this is the input, right? So this is Z0 input. You follow it by W1, right? This is the weights. This is a linear mapping, and then you follow it. It's followed by sigma 1. It gives you Z1, the input, the output of the first layer, and then this output, right? It's sigma 1 applied to W1 Z0. You feed it into the second layer, right? So now you have W2, and then the output of W2 goes into this nonlinear activation function to give you Z2, right? And which is sigma 2 applied to W2 Z1, right? And so on and so forth until you get the output. Sorry, this should show up actually. The output XJ, the last layer, the output of the last layer, basically. So from a signal processing point of view, this is a cascade of filters, right? And then for each layer, you have a filter and a nonlinearity.
So sigma is just the filter? Or
it's a function. It's a function. It's a nonlinear activation function, actually. And then we can talk a little bit about that later, actually. So it's a vector. It's a vector valued vector function, right? So it takes an input, a vector. Actually, it's here. Let me talk about it here. So as I was said, actually, the input of each layer, right, Zj, it depends linearly on the input from the previous layer plus this activation function. And here there's a bias which we can ignore for now.
So that sigma is just an f.
Exactly. Sigma,
function.
Exactly. It's mapped the r-dimensional space to the r-dimensional space. So it's a vector. You give it an input, it takes as input a vector, and it outputs a vector of the same size, actually. Yeah. And depending on which value you give to sigma, you end up with one function or another activation function.
But usually it's a type component-wise.
It's component-wise, exactly.
What is it?
Element-wise, exactly.
It says so.
Exactly, element-wise, absolutely. Exactly. So we apply it per element, actually. So basically, yeah. So actually, the output for the first one is the input of the first one as well. Exactly.
And it's the same function for each component.
It's the same. Yeah, it could be. I think it could be. Yeah, but I think it doesn't matter actually. They use that for notation to make the notation cleaner. I think it could be different.
But you see any benefit in that?
I have no idea actually. Yeah, this is why we should have like someone like Saikat and Arun here, or Ali Reza. No comment. Okay.
Can you see it as a process?
What do you mean by a process?
That Zj. Can you see it as a process in
like
terms of J
right.
index?
Right. As a stochastic process, you mean?
Yeah.
I mean,
It's
you could if you
non-linear,
assume.
non-linear.
Right. You could actually. You could. Yeah, exactly. But then you need to assume some distribution on the input. Actually, you need to assume some distribution on the input. Yeah. But you could do it. Yeah. But I mean, from a functional point of view, I mean, this is the definition basically.
But then if you put a distribution for the input, it's really hard to see what is even the first layer distribution output, right?
Exactly. Because I mean, as we're saying, it's a non-linear function actually. So even if you make some assumptions on the input distribution, exactly, absolutely. So even like getting the distribution at the first output layer is challenging. So absolutely, yeah. Okay, and then in the context of yes, and then we could also define something that we call h. This is just for the rest of the talk. So this function h is kind of represents the whole system end to end. So it represents the effective response. If you think about it again from a signal processing point of view, so it maps. It's the function that maps z0, the input, to the output zj, right? So we can call that h. So basically, this is kind of an effective response of the system, right? And actually, this is the function that we want to learn, basically. So the idea is we want to learn h by adapting these weights, basically. By changing the weights, we hope to learn this function h. Okay? Right. Just some ideas about what is the theory, what are they trying to accomplish, and this is also connected to what Ali Reza presented in Seminar 3. So this is like about approximation capabilities. Actually, let me move this one over here. Yeah, that's better. Right. So basically, the idea is that so neural networks are universal approximators. This is the main motivation why people are using them, right? And this was also covered previously by Ali Reza. So for instance, just to recap the result actually. So if you have a single layer neural network, right, with a nonlinear activation, it can approximate this function h that we are trying to approximate with arbitrary small error if you have the size of that hidden layer is large enough, basically. So this is the motivation. And then, which also, I think at some point we also had some discussion. So if one layer is enough, actually, why go for multi-layer, actually? And this is also taken from a nice chapter from this book, actually. So they have a nice discussion on like why like people are not using just single layer because they are universal approximators. And the idea is, so they're saying that when you're training this algorithm, so this desired function that you want to learn may not be learnable with your training algorithm. You may not achieve that function. That's the first reason. The second reason is that you could choose the wrong function because of overfitting. And this is the reason that people still go for multi-layer network, although from a theoretical point of view, this is like one layer should be more than enough. Right. Okay, some more results actually. So actually there are some results from this guy, Baron. They have actually some bounds on the size of these layers, actually, bounds on the number of layers, but the bounds apparently are very loose. So this is also in line with the result that Mikael presented like a while ago. So trying to get some bounds on the number of layers, the size of each layer. And then this is still very far away, actually. And apparently in practice, everything they do, the size of the layer and the number of nodes that you have in this hidden layer, this is determined experimentally. So you do that with cross-validation. activation, right? So something that looks like this, for instance, like this max function, 0 max. This one, it can represent the functions h, right? So this function that we're trying to learn that I talked about, they can represent a function h having an exponential number of regions in J. So if that function h is kind of, it could have exponentially many number of regions in that number of layers J. So basically, the more number of layers you have, the better you can, your representation power increases. So you can represent a bigger set of functions actually. So you can actually effectively learn H in a much better way. And then, of course, this is provided that you you have a mechanism for preventing overfitting, because I mean, the more layers you have, the more potential for overfitting. Right, and there's a nice insight by this guy actually. So he was talking about the fact that the motivation for deep neural networks is to assume that this function that we are trying to learn is a composition and a cascade of several simpler functions actually. So basically, by having, and this is what we're trying to capture with this cascade of filters. So this function h, you assume that it's a composition of several functions where each function is simple actually. And then this is what you try to do by having this cascade of filters. So we assume that your function is a cascade of linear filters actually, plus this activation function. So this is kind of an implicit assumption that the model that you're trying to learn has that structure or has that feature. I thought that this was a nice insight to mention. Right. Okay. So moving on to the fundamentals. So this is actually connects back to this learnability that we talked about in I think the second seminar. Yeah. And this is like basically going into more into this training actually, and then how does this connect to this empirical risk minimization? So if you have, let's say that we are given n training samples, pairs x1, xi, yi, right? And then each one is both are coming from a joint distribution, pxy. This is also kind of has been said in seminar 2, but this is more applied to these neural networks basically. And the goal here is, as I was saying, we want to learn that prediction function h, which models this whole system from input to output, and such that h of xi equals yi. So basically, for each sample, we can actually predict each sample correctly for all these training samples, so for all I. And then ideally, so we want to find the function h that minimizes the expected risk, or what we call the true risk actually. So basically, we want to minimize this risk, the expected risk of misclassification, which actually can be written in this form, right? So it's R is the expected risk. It's the probability that h of x different than y. So basically, we make a problem in classification. We have a classification error, and then we want to minimize that with respect to h. And here we are assuming that h is coming from a family of functions. It's a family of prediction functions, this calligraphic h. But the problem is, as we've said before, actually, the problem with solving this problem directly is that we need some information about this distribution, the joint distribution, and usually this is not available actually. So what people go for is exactly we go for a surrogate problem, right? Which is called like empirical risk minimization, right? So we assume that you have a training sample, you have a set of training sample xi, yi, and then you want to find the best function from these n sample that minimizes this loss function. And then depending on what choice of loss function, you end up with one optimization problem or another actually. So this is how we get from empirical risk minimization to, from this expected, so minimizing the true risk, the expected risk, to minimizing the empirical risk minimization. Okay, right.
Sorry,
Mm-hmm.
what is a small w?
Yeah.
What is a small w?
Small w. Yeah, sorry. Yeah. So this is just a simple way of representing all the weights that we have: w1, w2, w3, w4. Exactly. Yeah. So this is actually, so this function. Okay, maybe I should say a few words. That's good actually. So basically, this function L takes as input it takes as input x, I, and w, where w here represents all the weights. It gives you a prediction h, and then you see how far is that prediction with respect to yi, the true input, the true output, the true prediction, right? And then you try to minimize that, and it helps to think about. I think this comes up in the next slide. So we try to see some choices for that. So following slides. Okay. So also some some hints on how to choose this family of prediction function. Apparently, this set H, so here we are taking this function from a family of sets. So this is a constraint optimization problem. And the choice of this calligraphic H, which family of functions we want to use, is also important, actually. And here, actually, they give some guidelines on how to pick that. So basically, for instance, obviously, we want this function, this calligraphic H, to be picked in such a way that we achieve a low empirical risk. So the value of this empirical risk from the previous slide is low enough. So we can achieve that. So basically, by avoiding bias and overfitting. That's one. The second criteria is also kind of important. So basically, the idea is you want the gap between the true risk and the empirical risk to be bounded. Because so far, I mean, we talked about ideally we want to minimize the true risk, right? So this is the averages that we get in practice. But we use a surrogate problem. But then there should be a connection between the two. So what is the connection between the true risk and the empirical risk? There should be a bound on that gap. And that bound actually is kind of, you need something that looks like that, right? So you need a bound on the true risk minus the empirical risk. And actually, this is something that we get from Hovding's inequality that was covered before in seminar 2. So we can get such a bound actually by using Hovding's inequality. So it says that you fix an H, and then this happens actually. So there's a bound on the true risk versus the empirical risk, and that bound increases with n, and n is the number of samples, right? So that bound decreases as 1 over square root of n actually. But the problem with that is that it's kind of not so useful, because h, remember that h is the function that we are trying to optimize. So h is not known actually, so we cannot fix that. So this is a bound that we cannot really use. And then they go again and they argue, this is actually also part of that tutorial that we were talking about. So they argue that instead of using Hovding's inequality, people have used this VC dimension, which we also covered extensively in the second seminar. So this is kind of a nice motivation of why people have thought about these VC dimensions instead of like some very simple bounds. So this was kind of just a motivation of like why people have looked at VC dimensions, these kind of things. And then, of course, obviously, a third criteria for picking this calligraphic H is we want to make, because this will dictate the kind of optimization problem that we have. So the problem has to be tractable. So we have to pick H in such a way that we have a shot at solving the problem. Okay. So this was kind of a motivation of how do we connect, what was the connection between the true risk and the empirical risk. And now we go for the empirical risk formulation, and then going back to this idea, to the model of these deep neural networks, basically. Okay, so if we fix this, and if we get back to this empirical risk minimization problem, and then apply to this deep neural network, so we get something that looks like that. So the empirical risk minimization problem takes this form, right? It's a minimization of so basically, so this is yi and xi are the input training and the output training samples, the output of each training, and then you have a cascade of all these filters. So right, this is the output. So wj is the output actually of all these cascade of filters basically. And then this is the kind of problem that we have actually. And as you see from an optimization point of view, so this problem depends on w1, w2, and wj, right? So this problem is very complex, right? Because first of all, you have these couplings between the variables. So w1 depends w1, and there's a coupling between w1, w2, and etc. And there's also these nonlinearities. So that's a problem. So it's non-convex, obviously, and people have tried to address it with like first order methods, basically. So stochastic gradient, something that like what Sindri covered like a while back. And then the problem is that when you go for stochastic gradient, so most proofs that you have for convergence need the function to be convex actually, and this is not the case. So we lose those guarantees if we use stochastic gradient in these neural networks. That's a problem actually, but still people have learned to live with that. Apparently, they still do that. So of course, so this is the first challenge of working with stochastic gradient for these kind of expressions. And then the second one is how do we compute the gradient? So usually stochastic gradient or even gradient descent, you need a gradient of the function. And the problem here is that the gradient depends on these nonlinearities. This is a problem actually. And this is where backpropagation comes in actually. It's a mechanism to that gives you the way to compute these gradients, and then it gives you a structure to compute these gradients. I think this is the best way to see it. It gives you a systematic way to compute these gradients. And let's start with a very simple 3-layer network, actually. So here, as I said, x0 is the input. It's multiplied by w1, the first layer weights, gives you x1, w2, x2, w3, x3, right? So this is a simple example. And here, as I would say, the weight optimization happens with stochastic gradient or gradient descent. So basically, the weight for wj, right? So for instance, j here takes values 1, 2, 3, 1 or 2 or 3 because it's this in this small example. So wj is updated in the following way. So you take your wj equals wj, the previous iteration, minus alpha, step size, times the gradient of f with respect to wj. So you take a step in the direction of wj, right?
So do you iterate on each layer many times, or do you iterate each layer one time?
Actually, this is coming up next. This is coming up next. Exactly. So this is exactly what backpropagation is telling you. So basically, the problem is we need to compute this guy, right? So we need the gradient of f with respect to wj, right? This is the challenge here. And the problem is, as you see here, because of these non-activation functions, it's hard to compute the gradient. It's hard to compute the gradient, plain and simple. Because
it's like a sequential optimization. You know?
It's exactly. I mean, you do it layer by layer. Actually, you do it layer by layer. So you find the relation between the gradient at layer j, and you relate it to the previous layer, and then you hop back until you get exactly. So it's a very nice idea, because I mean, if you try to go for a brute force approach and try to find what is the gradient of this function with respect to w1, this is like very nasty. Yeah, it's very nasty because these things, and keep in mind that these sigmas might be non-differentiable.
Yeah,
that's a problem.
You need to ensure
so
continuity.
Exactly. Yeah. Okay. So this is the network, and then as I was saying, it's you start with the last layer actually. So here it's gonna get a little bit messy. So just like for the next couple of slides, just to see how these algorithms work actually. How do we do these? How do we crunch the numbers basically? Right. So here, as I said, we start with the last layer. You start with the output layer, and then here at the output layer we have actually two equations. Right. At the output layer we have x3 is equal to w3 x2, and then we apply sigma 3 to that. So this is the output equation. And then we also have the loss, f, in that case. So the loss function that we're minimizing is this y, the output. So the target, actually, as we say, and x3 is the actual output that we get from the training. And we want to minimize that distance, basically. This is actually a special case of this one. This is exactly what happens to that loss function when actually we go for that small network. Right. And then the main idea, so now we are interested in finding this gradient of f with respect to w3. And the problem, and here the way to do that is by applying doing several tricks with the chain rule actually, from calculus, not probability. So let's see these tricks in action basically. So here we are interested in the gradient of f with respect to w3. So the first trick is we apply the chain rule, obviously, right? So this gradient is equal to gradient of f with respect to x3 and gradient of x3 with respect to w3, right? So this is a simple application of the chain rule. And then now, so for the first part gives us, so as I've said, so this is the gradient of f with respect to x3. This is quadratic in x3. So this gradient becomes exactly this one. So basically you have the gradient of x2, it's a squared function of x3. So basically the gradient becomes 2x3. Plus some constants actually, so this is exactly this guy. And then we have actually, now we get up to this point, right? So we have the gradient of x3 with respect to w3, right? And then we do one more trick, so to speak. So basically here, now we need a way to find this derivative, right? Or this gradient basically. And now we plug in the equation for x3. As I said, x3 is sigma 3 applied to w3 x2. Just plug it in here, right? And this is what we end up with. Right? And here again, so this is, as you can see, this is a composition of two functions. So here we need the gradient of sigma 3. So here actually, this is a composition of two functions. So we have actually w3 x2, this is the first composition, and then we have sigma 3. So this is the derivative of a composition of two functions. So then from the chain rule, we can split it into two derivatives, or two chain rules. or two derivatives actually. So if we apply the chain rule again to that last term actually, so actually what we get here with some manipulations that we can skip actually, this is some very simple thing. So here we get actually sigma 3 prime, which I will talk about later. I will see what does that mean, times this, the gradient of W3x2 with respect to x3, with respect to W3. And as you see, this is linear in x2, so this gives us x2 transpose. And here I have called this term delta 3. And here actually, sigma 3 is nothing but, this is the derivative of each component in that activation function. So this is, as I said, this is a vector where the first element in that vector is the derivative of sigma 1 with respect to the first element, sigma 2 with respect to the first element. So we don't have to worry about that, this is not important. So this only depends, so basically this sigma 3 prime, those so sigma 3 prime, sigma 2 prime, and sigma 1 prime, let's get that out of the way. They only depend on the choice of activation. So basically this is like how fast does this activation function change with time actually, or with x. So we can forget about that.
And in the points where they are non-differentiable.
Exactly.
Because most of them.
Exactly.
What do you do with that?
Actually, there are some words that extend those to, you can actually express these chain rules in the context of subdifferentials. So basically, subdifferential is a way to handle these nonlinearities actually, the non-smoothness actually. So there are extensions to that. Yeah, there are some extensions. Right. So basically, this, I mean, it's kind of a succession of applications of the chain rule to get this one. And as I've said here, sigma 3, we don't have to worry about that. So sigma 3 prime is just, we can think about it as something that depends on the choice of activation function. So basically, this is what we end up with, right? So the gradient of f with respect to W3 is delta 3 times x2 transpose, where delta 3 is this thing. And here, when we have this circle, this is the Hadamard product. So basically, element by element. So here, basically, you take this one, and then this is a vector, and then you take its element by element product with sigma. That's it. Okay, so this was the application of this. How do we do backpropagation for the last layer, for layer 3? So now what happens when we do the second layer actually? So it's the same process, but here we need a bit more tricks actually, and then it's interesting to see why this is a little bit more complex. Again, so here at the second layer, so this is the output equation. This is the output of the second layer. So it's sigma 2 applied to x2 to w2 x1. And then we have also the output, right? So which is, we have actually the error, right? Which is minimizing y minus x3, the square norm. So those are the equations that we need here to get the result actually. And here we are interested again in the gradient of f with respect to x, w2. And here the first step is again an application of the chain rule. So basically going from this one, we go for gradient of f with respect to x3 and gradient of x3 with respect to w2. So chain rule simply. And then secondly, as we've said before, this term actually, this is quadratic in x3, so its gradient becomes 2x3 minus y, right? So this is linear, this becomes linear in x3. And then the second part, now we get to that point. We need the gradient of this one, x3 and w2. But exactly, and here we substitute you just substitute the value for x3, right? Which is this one. Sorry, it's actually in the previous slide. So x3 is on the previous slide. Just substitute the value, and then here again, so this is a differentiation. We need the partial differentiation of a composition of functions, right? So it's w3x2 first, and then sigma next, right? You apply this nonlinearity next, and then we can again use the chain rule to split it into the product of two gradients, right? Again, we get this one, and we actually end up now with the gradient of w3x2 with respect to w2. And then again here we apply another chain rule, right? And now with respect to x2, so we want to split this one into two derivatives. So the gradient of w3x2 with respect to x2, and the gradient of x2 with respect to w2. And this way to introduce the dependence on x2. We will see why actually. So now basically we have delta 3, right? So this is, recall from the previous slide that this quantity is actually equal to delta 3. So now we have delta 3 over here. And then the second part, so this is actually linear in W3, right? So it gives us W3 transpose, right? And then finally, we have the gradient of x2 with respect to W2, which again, we can do the last step of replacing the value of x2 by its value, right? And then we get another derivative of a composite of two functions, which again we can apply the chain rule one last time to get actually this expression. Right? It's actually delta 2 x1 transpose, where delta 2 is this thing over here actually. So there is a structure actually, and then we will see how next in the next slide. Yeah. So there is a way. Here the problem is that the further you go, as we see, so in the third layer, like it was more straightforward because you have to apply the chain rule once. Here you have to do more tricks because as you go deeper in the network, you have more dependencies actually. So you have to apply the chain rule more. You have to do some more tricks actually. Yeah. And the strange thing is that there is no. I tried to find some references for these equations, but there was not actually. So I ended up doing most of these things by hand actually. That was strange. We can probably bring this up at the end of the lecture actually. Yeah.
I'm just wondering, it's like X. So if you look at it's like the left hand side of the last equation. It's
Left
like
hand, yeah.
x1 transpose is equal to the subroutine. It's equal to itself.
Sorry, come again?
I'm just I think it's a bit weird. Like
Yeah. So you mean
so it's like
this last term?
Yeah, this last term is equal to x1.
This is equal to x1 transpose.
Oh.
Yeah, because this is a differentiation with respect to W2 actually. That depends on how we define the gradients actually, but that's fine. So basically this is linear, so W2 x2 is linear in W2. So when we take the derivative, you end up with x1 actually, because you're taking the derivative with respect to W. Yeah. Okay, so this was the point actually. So as you go further in the network, you have to do more tricks because you have more dependencies until you get to the final stage. So now at the first layer, we have to actually, it's a little bit more tricky than that, but then we're not gonna suffer through those derivations. So at the first layer, after some number crunching, we end up with a very nice structure. So it's always actually delta 1 times x0. So basically there is a repetition. And if we want to put that into general form, basically now let's go back to the full network. So when we have all the layers basically. So how does backpropagation work? So first you compute this cost function for all across all the layers. So you compute it at the output. So basically it looks like something like that. So here you give it like one pair of training example, x0 and y, and this is the cost function that you minimized, right? And then to compute these gradients, actually, the gradients has this very nice closed form expression without being actually closed form. So this is actually depends on delta j, it's parameterized by delta j and xj minus 1. And as I said, delta j also has this recurring pattern actually. So this delta j that we defined previously takes this form actually. It depends on wj plus 1, so the filters in the next layer, and sigma j prime, which depends only on the choice of these activation functions. So there is a repeating structure. So this is nice actually. And then, so after you found these gradients, you do this update actually. And this is to answer Mikael's question actually. So this update actually, you do it on per layer actually.
Once per layer.
Once per
and
layer.
then
Exactly.
again.
And then again. Exactly.
I see.
Exactly.
So, yeah,
Yeah.
starting with the last.
Exactly. So in a sense, like it gives you this backpropagation is not. It just gives you a way to compute the gradient actually, and then the way to, and then after you have the gradient, you can use the way you want it. And this, I think, I'll try to cover that in the next slide. So basically, different ways on how do we use this gradient information. How do we do these updates?
How about initializing the weights? Or is that only? Is it art only, or is there some science?
Yeah, I don't know.
I tried it random, but it didn't
Yeah.
work, so I don't know.
I think usually, like when you have these kind of non-convex problems, the choice of, like whenever you have a non-convex problem, this is also my experience with some other topics, not necessarily neural networks. So basically, when you have a non-convex problem, you have many local optima, and then possibly many global
So you
mean.
should
So the best,
initialize randomly, perhaps
so what,
7,000.
exactly, and then take the
times
best.
and then
Take the best. This is, I think, what people do. But maybe this is too expensive here.
Oh, just
This
like
takes
one
too much
of
time.
Things. The first thing is that there is something called transfer learning, where you try to learn these weights using some other data set somehow offline. And then once you want to apply this to some other train to some other neural network, almost the same
Yeah.
structure, then you can initiate with those.
But then you know, also
Yeah.
you will end up in a local minimum that's
Yes.
close to.
Exactly.
Something like that. But
Like,
that's the
yeah.
first thing. The second thing, I saw some paper that they are talking about the local minima here, and apparently the good thing is that it's almost doesn't matter from which starting point you start. You will end up to some equally good local optima, something like that. So the local optimas are like dense around the global optima, something like that.
Right.
At least
Yeah.
this is the common belief. That's why that they don't really care about where they start. It will affect the convergence
Right, yeah.
speed, but at the end of the day, they will converge to some point that they
Yeah.
will be satisfied with.
Yeah. And then in terms of analysis, like, I mean, in terms of like things you can claim and then prove, when you have these kind of problems, non-convex, highly non-convex with like many local minima, you cannot do much actually. You cannot say anything about like exactly about like where you can end up, which local optima you can end up with actually. So I think at best, I mean, best case scenario for this kind of algorithm is that you can show that this will converge to a stationary point, not even local optima, at best, because of this nasty structure in the cost function. So basically, as I was saying, the problem here is that I did not find any standard reference to do these computations, to do these calculations. And then this could be something that we could think about actually, some areas for where we could potentially think about having some collaboration. So basically, there is no standard framework for deriving these equations. So if you think about, when I started to find some references on backpropagation, the problem was that you can find it for very small, like the single layer network. You can find many references for that. But having like a complete theory that tells you that, okay, this is, I mean, that gives you a framework for doing those. It's completely absent actually. I had to do these by hand actually. Yeah.
But
So
how MATLAB is computing that?
Or
Or any
MATLAB?
other software, how they do compute this backpropagation? For
backpropagation.
like 100 layers.
No. They have it. Of course, it's implemented actually, but there's no. I was talking about the mathematical framework. That's the problem. So they have some special cases that, okay, if you're using this L2 loss, this is what happens. This is how you compute these gradients. But there is no general framework for having that, like for arbitrary f actually. And then you say, okay, now I let f be this L2 norm. What happens here? Now I let f be this like MSE or like L1 norm. This is what happens actually. Yeah. So something that is more standard, more systematic. Yeah. Okay. So exactly. So as I was saying, like backpropagation gives you a way to compute the gradients. That's it. But then once you have that gradient, there are many ways to use that gradient. So for instance, like one trade-off that they talk about a lot in these papers is whether you go for stochastic optimization or batch optimization. And this is what it means. So if you think about batch or the second seminar, with batch optimization, you use the full gradient, right? So at each update, you take the gradient of f with respect to wj, and then here the gradient of f is, this is the gradient of the cost function with respect to all the training samples. So basically here this gradient requires you to know all the samples, and you need to compute the gradient with respect to all these samples. And that's a problem, right? This is the problem because then you need too many, then computationally it's very problematic because you need to compute the gradient with respect to all the samples. So basically, if you have too many samples, this does not scale well. What happens on the contrary, right? So here you get this classical. So here you get this like this phenomena where your function is monotonically decreasing because at each iteration you can be sure that you are decreasing the function.
Doesn't that depend on alpha?
Depends on no. In any case. Of course, I mean, you have to pick alpha between 0 and 1,
Yeah.
but as long as you do that, it's always going to increase. Because this step that you take, this gradient expression, this can only decrease your function. If you pick alpha between 0 and 1, of course, if you pick alpha to be 2, no, yeah. Right.
Okay, but just with respect to WJ.
With respect to WJ, exactly.
So you can make sure that the globally is decreased. You can just make sure that it will decrease
Exactly,
in that
exactly.
specific.
Because you are taking into account all the geometry of the function, all the
On that
topology.
specific direction.
Exactly. So actually, I think I have.
This is a
picture
single
somewhere.
coordinate distance.
Yeah, this is actually this is exactly what should. So here, let's look at the blue curve actually. So here with, okay, let me first cover, let me talk about steepest descent and then the other one, and then we can go illustrate, talk about the differences. So basically, as we're saying here, like you can be sure that at every iteration, if you pick your step size, if you pick your step size optimally, so to speak, then you can be sure that this will decrease, because here what you are doing is you are taking the geometry of the function into account, right? Because here that every step that you take takes into account the geometry of your function globally, because you are taking all the samples. But the problem is that this is computationally complex. That's the limitation.
But why is it called batch? Why?
Batch, because here you do that in a, here you use the whole batch, your whole training batch, which, and so there is something that they call batch training, and then you use the whole training set for that. There's something that is called mini batch training, and then you use a subset of these. Yeah. So the alternative is, as to say, is let's not use the full gradient information, and then what happens in that case? This is what they call stochastic optimization, or stochastic gradient in a sense. So basically, instead of doing the gradient step, computing the gradient step with respect to all the samples that you have, you actually do that for one training sample. So you pick a training sample at random, and you compute the gradient with respect to that. So you have n training sample, pick an index at random, right? Let's say here index I, and then compute the gradient with respect to that sample only.
So no one is doing second order?
There are some extensions, actually. There are some extensions. Actually, there are people that have, what do they call it, Newton-type methods. So they do acceleration based on second-order statistics, absolutely, yeah. So I think we're going to cover that at some later stage. Yes. So here the advantage is, as I was saying, the advantage here is that this is scalable, right? Because the computational footprint is very small, much smaller than when you use the full gradient. So this is the motivation. And I think in terms of usage, this is much more used than gradient descent and all its derivatives because of that specific requirement, because of that specific advantage. And here, as I've said, like because the choice of indices is at random, so here we have convergence. Actually, convergence happens in expectation. So basically, you can ensure that on average, these iterations will converge to that point where the derivative becomes zero, where the gradient vanishes. This is the kind of results that you can aim. And visually, this is exactly what happens. So the blue thing here is, so these are some contoured lines. So the blue one here, this is gradient actually. So at each step, you go in a direction that is orthogonal to the contour lines, right? Until you reach that point. And then you're always getting, with each step, you get closer and closer to the point. That's why you have this monotonically decreasing nature. Whereas in stochastic gradient, you're not sure about that. Because at each point, you're not sure that you are decreasing your cost function because you are looking at one sample only. So you are taking you are not taking the whole structure into account. These contour lines, you're not taking them into account actually. So basically, and this is actually going to be covered extensively in the next seminar, stochastic gradient, I think. Yeah, much more details. But this is just to set the stage. So I mean, in a sense, this is kind of how to exploit this gradient information. So we spent a lot of time on like deriving these backpropagation equations, and this is just to see like, okay, how do we use them in practice actually? What kind of choices do they have to make? Okay, some practical issues, not from my research. This is just from a few papers that we sampled. So the problem is that people think that still backpropagation, even when you use it in conjunction with steepest descent, or when you use it in conjunction with stochastic optimization, it's still computationally demanding, especially when the number of layers increases. There's a problem with the vanishing gradient, so we talked about that before, and the problem is how to avoid overfitting actually. So these are some real-world problems that people have tried to address actually, and with some success. Some taxonomy I think we don't have to worry about. So different types of neural networks actually. So there is actually everything that we talked about before. This model that we use, this is called feed-forward neural networks. So in a sense here, the communication happens from output to input, right? So you have propagation in the forward direction only. So this is what they call feed-forward neural networks. So basically, the model that we're using today, there are some variations on that. So for instance, you can think about convolution neural networks. So in a sense where your signal, your vector, your input gets convoluted at every layer with a different weight actually, with a different filter, so to speak. And in that case, actually, this matrix W becomes a circular matrix. So it has some structure, actually. It has to fulfill this circular property. And then there's also something that is called fully connected networks, where you have a connection from every input layer to every hidden layer. You have this is what they call them fully connected. You have something that is called recurrent neural networks. They allow for loops in the network, so you can have you could have links that propagate in the forward direction. You can have links that propagate in the backward direction, etc. Okay, this is loosely based on actually this one, those first three papers actually, and mostly this first one actually. This is a very nice tutorial actually, from the first 2 chapters of this one, and then there's a chapter from this deep learning book. This was also very insightful actually. So this is where they were talking about this representation power of neural networks, the fundamentals as well, and back propagation from this famous paper by LeCun and Boutou. Okay. I hope that was not too much in terms of like the derivations, too much number crunching. Okay.
No.
Yes, so I mean, there's something, there was something weird that I found, like when I was preparing for these, there's no standard framework that allows you to do this gradient derivations in a systematic way. What? Sorry. Ah, yeah. Okay. Ah, this is still on. Ah, no, it's okay. We can turn it off now. We can turn it off. That's okay. This is discussion. This is the discussion part. Let's not give people ideas.
But if people watch this video,
no one, yeah. So this was a little bit strange actually, and probably maybe like one thing to think about. Yeah, I mean, like in terms of like, this is something that we see a lot in like signal processing. My background. So the idea is that there's tons of work that allows you to deal frameworks actually. To deal with like complex derivatives and have a framework for deriving functions. So you have some assumptions on the function, and then okay, this is how you do these computations basically. You have a framework for that. You have a systematic way. But the problem is that this is missing here. So this is something that I was thinking about actually. So like let's say okay, we make some assumptions on the function that we have. So it's smooth basically. It doesn't have to be smooth even, I think. And with this specific architecture in mind, when we have these multi-layered neural networks, okay, this is how the gradients looks like with respect to W1, this is how it looks like with respect to W2, for kind of arbitrary losses actually. When your function, you don't specify the function, because here those special cases that I was able to derive by hand, this is like for very special cases actually.
But you can sell this scheme as a dynamic gradient.
Yeah, exactly. In a sense, yeah, it is. I mean,
it's obligations in this.
Yeah,
so
absolutely.
It's like,
yeah, absolutely. So I mean, it's just a way to. It gives you kind of a method to compute these gradients, basically. Yeah, in a more systematic way. Yeah.
But there are, I mean, a lot of works at least in stochastic formula, they use this dynamic program.
Yeah, but this is a little bit different actually.
Yeah, but the idea.
Yeah, the idea
is like this.
Exactly. To try to exploit some structure, this layered structure, and then absolutely. Yeah. So just some food for thought.